Hi, everyone. Welcome back. So today we're starting a new section of the course on minimum spanning trees. So I think we'll probably spend the next 4 lectures on this topic. The first lecture will be almost entirely deterministic. So very little mention of randomness, just general theory about minimum spanning trees. The second lecture will mostly be focused on minimum spanning trees on infinite graphs and what happens in the Euclidean setting. And that will allow me to develop the connection with percolation and critical percolation. Lecture 3 is going to be focused on the global structure of the minimum spanning tree in the mean field case, where the underlying graph is a randomly weighted complete graph. And then the fourth lecture, I'll be focused on both the weight of the minimum spanning tree and also on its local structure. So that's the plan. If my lectures go slower than planned, then maybe it'll take me a little more than 4, but I hope to stick with roughly that plan. So let's get started. Feel free to ask questions as usual, either in the chat or by unmuting yourselves. So the basic object that we'll be considering the whole time we're studying minimum spanning trees is a weighted graph. I guess usually connected, so a weighted graph. So G, and the sort of generic notation for weights. So this is some vector which puts weights on the edges of the graph. And these weights will always be non-negative. Okay, and then so the underlying graph will usually be connected and finite, but there will be exceptions to those conditions, in particular in the second lecture. Okay, so given such a, given a graph in general, a spanning subgraph is so just a subgraph with all of the same vertices and some of the same edges. So that's a graph H, which is VE prime with E prime contained in E. Okay, so there's no requirement for a spanning subgraph to be connected. Indeed, in this definition, there's no requirement that G is connected. It just says keep all the same vertices and keep as many or as few of the edges as you like, but you're not allowed to add in any edges that weren't there in the first place. Okay, then a spanning tree. So is a spanning subgraph that's a tree. Okay, so if G, a graph has to be connected in order to have a spanning subtree. And then a minimum spanning tree is so it's a spanning tree which minimizes the following quantity. So the weight of T, which is defined to be the sum over edges of T, of the weight of the edge, over all spanning trees of G. Okay. So the weight of a spanning subgraph or a spanning tree is just the sum of the edge weights on that spanning subgraph, and a minimum spanning tree is a spanning tree of minimum total weight. So sometimes people write MWST instead of MST, but I'll say MST. The weight, it's always with respect to some weights, which will always be either obvious in context or explicitly spelled out. Okay, so here's since today is mostly about deterministic properties, I want to start the lecture by showing you some pictures of random minimum spanning trees, just to give you the kind of flavor or the idea that something interesting is going on probabilistically, that there's something to say in the random setting. So this is the first picture. It's the minimum spanning tree of geometric graph. So here the graph is formed by sprinkling 100,000 random points and then forming their Delaunay triangulation. If you don't know what that is, it's effectively, well, I won't get into it, but the graph is drawn, there's some planar graph that's drawn. It's a triangulation. It has a bunch of little gray lines that you can see all over the place. So the distances in this picture are just Euclidean distances. So that's how the weights are given to the edges. The weight of each edge is the Euclidean distance between its endpoint. Okay, and then lots of the edges are gray, but some of them are colored, and that's forming the colors that you see in this picture, the sort of rainbow pattern. Those are the edges of the minimum spanning tree. So there's sort of too many points for you to see the edges in very much detail. And so what the color coding is doing is telling you about the graph distance in the minimum spanning tree from a particular root node, so the vertex of label 1, say, which is a sort of slightly bigger black dot right there. Okay, so that means that points that are in red have a short distance in the minimum spanning tree to this root node. Points in purple have a very far path, and these sort of interfaces that you see are regions where people who, if you imagine this as a road network, people who live over here would be quite unhappy that to drive to the route they have to sort of do some long circuitous network going over here, whereas people just on the other side of this boundary have quite a direct route to the route. Okay, so very little is known rigorously about this picture. In particular, you see that, there's some interesting sort of fractal properties that are showing up with these interfaces. No one can really say anything about that as far as I'm aware so far. There are models, there are Euclidean two-dimensional models on the triangular lattice, so variants of this for which a little more can be said rigorously. But this particular picture is sort of beyond our current set of tools. And now, so that's one sort of picture. The next picture is what happens on the complete graph, where you take sort of independent uniform weights from the minimum spanning tree. So if I drew this, if I first picked an embedding of the complete graph of n vertices, and then picked the minimum spanning tree, you would just see a tangled mass of lines going every which way. It's not an intrinsically sort of nicely embedded low-dimensional object, so that sort of a drawing wouldn't look good. So instead, in this drawing, first the tree is formed, and then some nice embedding of the tree is picked. So that gives some sort of reasonably interesting drawing of a random tree. It's sort of less clear that how immediately the drawing connects with the geometric properties or structure of the tree. So this tree this also looks a bit less fractal because it's smaller. It only has 3,000 vertices instead of 100,000, I think. But I didn't generate a new simulation for the talk, so I didn't have a big picture to show you. Okay, but again, there's sort of something, there's something to understand here. you can sort of already, just by sort of staring at the picture for a while, start to get ideas for the sorts of questions one might like to ask. The colors in this drawing have to do with the weights, the underlying weights of the edges. So one thing you could do is delete all of the edges which are reddish and see how much that fragments the tree. And so by doing, asking various questions like that, you can start to formulate mathematical conjectures. Okay, so we're heading towards sort of trying to understand more things about both of these pictures, and we'll spend more time on this one than on this one, but lecture 2 will be at least partly about this more colorful picture. Okay, so that's those pictures are sort of by way of motivation, but we won't get to the details until later. I see a question in the chat: is this tree 3 regular? So maybe you can tell me which tree you mean. Do you mean this very colorful tree or the other? Okay, so this tree, I mean, isn't literally 3 regular, but in the it does turn out to be true that if you only look at the sort of macroscopic branch points, then you only see trifurcations and not branchings of higher degree. So if you sort of only care about, say, branch points which have at least 1% of the vertices in every direction, then you would never see a branch point of degree higher than 3. That's a theorem. Okay. Any other questions about the drawings before I go on to the sort of more pedestrian setup about MSTs? Okay. So the first, important fact about the minimum spanning tree is that it is quite generically the minimum spanning tree. So not a minimum spanning tree. So if this is to say that if G is a finite connective graph, and the edge weights are all distinct, then there's a unique minimum spanning tree. Okay, and the proof of this isn't very hard. So we'll argue by way of contradiction. So let's suppose that we have 2 distinct minimum spanning trees. Okay, so if these are distinct, then we can find some edge which is in one but not the other. And let's just take the smallest weight edge with that property. So let E be the smallest weight edge appearing in exactly one of T and T prime. Okay, so let's say that E has endpoints U and V, and that it's in T and not in T prime. Okay, so here's the edge UV. Okay, now because both trees span all of the graph G, there has to be some path between U and V in the tree T prime as well. Okay, it isn't this edge, but there's some path connecting U and V and T. So let's consider that path. I'll call it gamma. From U to V in T prime. Okay, so here's gamma. Okay, now the path gamma can't all be in the tree T as well, right? Because T contains this edge. If T contained all of this path, then that would form a cycle in the tree T, which it doesn't have because it's a tree, it's acyclic. Okay, so that means that we can find some edge E prime, an edge of gamma, which is not an edge of t. Okay, so that's some edge over here, E prime. So this is in E of t prime minus E of t. Okay, now we chose E to be the smallest weight edge, which was in exactly one of the trees. Okay, and here's so E prime is some other edge in exactly one of the trees, which means that it has weight bigger than E. Okay, so the weight of E prime is bigger than the weight of E. Okay, but then we can just swap out in the tree. So the blue path was part of T prime, right? But if we swap out the edge E prime for the edge E in T prime, we get another spanning tree. Anything that was connected before by going through E prime is still connected just by routing the other way around the cycle and going through E. Okay, so then that's saying the tree T prime, which has, so it's T double prime, which has the edges of T prime, except that we remove E prime and add in E. So this is another spanning tree. And its weight is what? So it's the weight of T prime minus the weight of E prime plus the weight of E. And we've just, that gives us a net gain because the weight of E prime was bigger than the weight of E. Okay, so that's less than the weight of the trees that we supposed were minimum spanning trees to start. Okay, so that's a contradiction. Okay, so that's a sort of easy proof by contradiction that that minimum spanning trees are unique. Okay, and so what I want to do next is talk about one of the first things that was studied in the area of minimum spanning trees, which is how to build them. They're really one of the first objects and prototypical objects in the area of combinatorial optimization. And they have the very nice property that algorithmically, just about anything, sort of any idea you have for trying to find them works. We'll actually use, so I'll describe and then we'll use 3 different procedures for building minimum spanning trees. The first one I'll tell you about is a sort of globally greedy procedure for finding them called Kruskal's algorithm, which goes back to 1956. So here's how Kruskal's algorithm works. We're going to be given as input a finite connected graph. And then edge weights as before. And let me assume that they're all distinct. Okay. And the procedure works like this. So you start by just listing the edges in increasing order of weight. So as E1 up to E number of edges. Okay. And then we're going to build a growing sequence of forests, starting from the forest. So a growing sequence of spanning subgraphs, if you like. We'll maintain that the subgraphs are always acyclic, so forests, starting from the empty subgraph. And we're just going to consider the edges in order. And whenever we can add an edge while maintaining that we have a forest, so without creating cycles, then we'll add it. Okay, so that's a greedy procedure. So we start with at time 0 we have no edges. So S is going to be our name for the edge set that we're growing, and at time 0, the spanning forest has no edges. So it's a VS0. Okay, and now we do what I just said in words. So for each step I from 1 up to E, so if EI joins distinct connected components, I just would say components of Fi minus 1, then we'll set SI, then we'll add that edge. So we'll set SI to be SI minus 1 union EI. Okay, and otherwise we'll just leave we won't add the edge, so we'll leave the edge set as is. Okay, and then we'll set Fi to be the forest with edge set SI. So we go along adding the edges one at a time. We only add edges if they don't create cycles. Okay, right? Because if the edges that don't create cycles are the ones that join distinct connected components of the growing graph. And then at the end, we output the final forest, which will be a tree. Okay. So let's just do a very quick example. So let's think about the complete graph with 5 vertices. Let's say 7, 8, 9, 10. Okay, so with these edge weights, so I'll just consider the edges one at a time. The first edge, so at the start there's no edges, and as we go, I'll highlight the edges we add in green, and then we don't add in orange, say. So the first edge gets added because we start with no edges, so the endpoints are in distinct components. The second edge also gets added because the current components are this component and then 3 isolated vertices. So this edge gets added. Third edge also gets added. It hooks in a new vertex to this component we'd already created. The fourth edge doesn't, here's the fourth edge. Its endpoints lie in the same component, so it doesn't get added, right? Same with the fifth edge. Its endpoints lie in the same component of the yellow graph. It doesn't get added. The sixth edge does get added. Okay. And now, in fact, we don't need to continue the process because the subgraph that we've of edges we've added already spans all the vertices. We have a spanning tree, and so any of the remaining edges will have both endpoints in the same component. They won't get added. This one doesn't get added. This one doesn't get added. This one doesn't get added, and this one doesn't get added. Okay, is the process clear? Right. So let's argue that process really does build the minimum spanning tree. Okay. So the output of Kruskal's algorithm is the MST of G. Okay, and so the sort of key step, the key observation for this connects what happens in this process that I just described with a simpler process where we start by listing the edges in increasing order, but then we just add them one at a time. We don't do there's no if then, we just think about the sequence of graphs we get by adding the edges in increasing order of weight, like we did in the discrete error-to process if you were attending that lecture. Okay, so let me write EI for the set of edges, which is just the I smallest weight edges, and GI for the graph with that edge set, so the spanning subgraph of G with that edge set. The limit is that if the edge EI joins distinct components of GI minus 1, then it's actually an edge of the minimum spanning tree. So this is, I'm introducing on the fly this notation, MST of G for the minimum spanning tree of G. Okay, there's a question in the chat. If the weights weren't distinct, then this process still gives an MST. If the weights, yeah, then I have to, break symmetry by, if I want a total order here, then there's ambiguity in what it is, because there are multiple orders that are non-decreasing. But yes, it still gives an MST if the weights aren't distinct. And it still gives something if the weights are negative, but then it doesn't have to be a tree. No, it does have to be a tree, but it isn't the minimum weight spanning subgraph in that case. Right. So I'm claiming that any edge, if we look at the edges in increasing order of weight, then any edge which, and think about adding them all rather than doing the censoring that happens in Kruskal's algorithm, then any edge that joins distinct components of that graph is actually an edge of the MST. Okay, so let's prove that. So let's think about. So what am I going to do? I want to think about an arbitrary spanning tree, okay, and then say that if it doesn't contain one of these edges of the kind in the lemma, then I could again swap out the some edge of the tree for for an edge of the type in the lemma and get a lower weight spanning tree. So if I could always, by swapping in an edge of this kind in the lemma, get a lower weight spanning tree, then every edge like that must be in the minimum weight spanning tree. Okay. So let's start with an arbitrary spanning tree of G, and suppose that this edge EI, like in the lemma, is not an edge of T. Okay, and let's look at the again at the path between its endpoints in the tree. Okay, so what's the picture? Here's the edge UV. Okay, and now I'd like to draw the components of the graph GI. Okay, so these blobs I'm drawing are the connected components of GI minus 1, right? Because I know that this edge EI joined distinct connected components of GI minus 1. So here's 2 of those components, and then there can be some more, right? And the path. So what's the path gamma? Let me draw it in blue. So the path gamma is some other path between these 2 vertices. So maybe it does something like this, right? It has to pass through, because these are in distinct connected components, it's going to have to at some point jump between connected components. It could do so several times, but it has to do so at least once. Okay, then so then gamma contains at least one edge joining distinct. Let me call it E components of GI minus 1, right? And so it can't be the edge EI, because we said that EI was not an edge of T, right? So that means that the weight of E is bigger than the weight of EI, because EI was the the edges are in increasing order of weight, and this is, so we've, inside of these blobs, that's GI minus 1, we've added all the edges E1 up to EI minus 1. Then we have EI, the next smallest weight, and then all the remaining edges joining distinct components have higher weight, right? And so that means that, again, we can swap out in order to get a tree of smaller weight. So then the tree T prime, which is T minus E plus EI, has smaller weight than T, and so T is not the MST. Okay, so why does that conclude the proof? I've just said if we have, for an edge which joins distinct components of the, if EI joins distinct components of GI minus 1 and T doesn't contain EI, then T is not the minimum spanning tree. Well, that means the minimum spanning tree does have to contain EI. Okay. I think there was some chat about negative weights. I shouldn't have mentioned negative weights, but my point was just that the minimum weight spanning subgraph need not be a tree, right? If all the weights are negative, then the way to get the smallest weight is just to add all the edges, okay? The algorithm still builds a tree. The algorithm only depends on the order of the weights, so it always builds a tree. But it won't be the minimum weight spanning subgraph if the edges can be negative. Okay, good. Any questions about the lemma? So I'd like to use it to show that the output of Kruskal is actually the minimum spanning tree at this point. Well, let me just actually, I mean, the proof isn't that hard, but I'd like to state, to sort of state one step of it as a corollary before I actually sort of do the finishing stroke. So this is really just, an immediate consequence of the lemma. So if I write S for this set of edges, so where the endpoints are in distinct connected components, so that's saying that the component of U in GI minus 1 is different from the component of V in GI minus 1. Okay, then S must be the edge set of the minimum spanning tree of G. Okay, so I'm saying, so the lemma told me that any edge that joins distinct components of GI minus 1 was an edge of the MST. And now I'm saying something slightly stronger, which is that the set of edges which join distinct components, oh, that should be not equal, sorry, that join distinct components of GI minus 1 is exactly the edge set of the MST. Okay, and so how do we see that? Well, so the lemma tells us right away that that S is a subset of the edges of the MST, right? The lemma precisely says that any edge in S is an edge of the MST. Okay. But I claim that that's enough because of the size of the set S, right? So if I write n for the number of vertices of the graph, then S has to have n minus 1 edges in it, because at the start we have a graph, so G naught, the graph with no edges, has n connected components. And the graph we finish with, G with all the edges, is, well, that's just G. It has one connected component, right? And each time we add an edge of S, it reduces the number of connected components by 1. Okay, so the number of components of GI is equal to, it's equal to the number of components of GI minus 1 if EI is not an S, and it's equal to the number of components of GI minus 1 if EI is an S, right? The edges of S are precisely the ones that join two two distinct connected components of gi minus 1. So those edges cause the number of components to decrease by 1, the other edges don't, and that number has to decrease from n down to 1, and so it must decrease exactly n minus 1 times. Okay, so S has size n minus 1, and the minimum spanning tree has n minus 1 edges, right? Because it's a tree with n vertices. So that means they must all be in S. We have a subset of the edge set, but it has the same size as the edge set. Okay. I see a question in the chat. Is that CG I minus of U? So that's I minus 1. So I'm saying the edges that join distinct connective components of GI minus 1. Okay. And this, so now, now we can prove that that Kruskal's algorithm is indeed generating the minimum spanning tree. What is that symbol? Is a C and not an E? Yeah, I'm sorry. My script C's sometimes turn into E's. They should be like that, but they're often like that. Right. So the key here's the key is the following. So the connective components of Fi and Gi are the same for all I. Okay, and this might seem clear to you already, just from this fact that the edges that the edge set consists of edges that join distinct components of G. But let's just let me quickly justify the claim to you with a picture. So let's think about what happens if inductively. So it's true when it's true if I is 0, then they both just have n distinct connected components, which are all isolated vertices. Okay, and then so inductively, if EI is joining distinct components of GI minus 1, so here are the components, then it's also by induction added. It's also joining distinct components of Fi minus 1. Then it's added by Kruskal's algorithm. Right? I mean, so if you imagine these blobs are the components of G, and then Kruskal's been going along building some trees at time, this is sort of the picture at time I minus 1. At this time, we know that the component sets are the same for both, and then this edge EI comes along. It is connecting distinct components of both G and of F, but that means Kruskal will add it, because Kruskal adds an edge whenever the edge joins distinct components. Okay, so that maintains the equality. So the components of GI are the same as the components of Fi. Okay, and on the other hand, if the edge falls within a component of GI minus 1, so an edge which does not get added by Kruskal's algorithm, so falls within a component of GI minus 1, right? Then its addition doesn't change the component structure. whether you add it or not, leaves the component structure unchanged. And so again, equality is maintained. Okay, so in short, I mean, the short way of saying that is just that the edges that aren't added by Kruskal's algorithm are precisely the edges that it doesn't matter whether or not you add them. The set of connected components remains the same. So, so the two processes then always have to have the same connected components. Okay, and by the same connected components, I just mean that if you think of the components as giving you a partition of the vertex set of 1 up to n, then those partitions are the same whether you look at the G process or the graph process or the forest process. Okay, obviously the edge sets aren't the same because edges like this get added by the graph process and not by the forest process. Okay, right, but that means right, but then you know that this claim says that the edges that are added by Kruskal's algorithm are just the edges that join distinct components of GI minus 1, because those components, it doesn't matter whether we talk about GI or FI for determining which the component structure is. Right, so Kruskal's algorithm always adds an edge if it joins distinct components of FI minus 1, but that's the same as saying we add an edge if it joins distinct components of GI minus 1. And we already said that the set of edges of the minimum spanning tree are those that join distinct components of GI minus 1. Okay, so that means Kruskal just outputs the edge set S. Okay, so so that says that Kruskal's algorithm outputs V with the edge set S, which is the MST. Okay, so so that's a nice, clean, and not too complicated fact. I want to leave you as an exercise of a slight strengthening of the fact that Kruskal's algorithm outputs an MST. So this is just saying that all of these yellow trees that it creates along the way are actually also minimum spanning trees of whatever it is they happen to span. Okay, so that is for each I from 0 to E, and each connected component, we call it H, of GI, there's a component TH of FI, which is the minimum spanning tree of H if you just take the natural set of weights for H, so with weights. The original weights just restricted to H. Okay, so everything that Kruskal's, all the spanning trees that Kruskal builds along the way are also minimum spanning trees. Or as Lior said in the chat, you could say that FI is a minimum spanning forest for GI. Yes. Okay. Any questions about Kruskal's algorithm? So we're about to dualize Kruskal's algorithm, but we're not going to do that directly. First, I'm going to the way I'm going to do that is by indulging in kind of the mathematical impulse to generality, which, when you see a nice, clean, provably correct procedure like this, it's kind of natural to ask how, in what generality it applies. So when do global greedy algorithms like this build minimum spanning structures? Okay, so that's the next part of the lecture. So I'll call it the generality of Kruskal's algorithm. So so I'll tell you, I'll define right away the sort of kinds of systems we're going to be looking at. So we'll call them independent systems. So this is just a pair, so a ground set and a collection of subsets. So X is a set, I is a collection of subsets of X. And to be an independent system, it needs to satisfy two properties. So I is non-empty, and it's downward closed. So that means that and if you take an element of I and you take a subset of that element, then the subset is also an element of I. Okay, so like independent sets, linearly independent collections of vectors have this property, right? If a set of vectors is linearly independent and I take a subset, it's still linearly independent. Okay. Spanning forests of a graph also have this property. If I take a spanning forest and I remove some edges, then I get another spanning forest. Okay. So the definition is almost finished. So an independent system is a matroid if it satisfies one more property called the augmentation property. So that's the third property. So this says that if we have two sets in our independent system and one of them is bigger than the other, then we can take an element from the bigger set. There's some element we can take from the bigger set and add it to the smaller set and get another set in our independent system. Okay, so again, if you think about collections of independent vectors in a vector space, that's the kind of canonical example of this. If I give you a set of 5 linearly independent vectors and a set of 6 linearly independent vectors, then there's at least one of those 6 can be added to the first 5 to create a larger independent set. Okay, so the maximum. So this definition dates back to 1935, and it was precisely to try to abstract away from the some of the sort of fundamental properties of say full rank matrices, which is where the term matroid comes from, but of this, like the column, the properties that say the column spaces of matrices would have. So the maximum independent sets of a matroid are called its bases. Okay, so I'll write script B for that. So this is right. So in this, there are some people put finiteness conditions on in the definitions of matroid. So I'm not doing that, but in most of the examples, that we'll see, the ground set is actually finite. So then, in particular, all of the independent sets are finite. So they're sort of finite dimensional. Right. So in this definition, I haven't put a requirement of finiteness, but I basically always will be in finite settings. So let's go through a couple of quick examples. So the sort of fundamental one that I already mentioned is if you take a finite dimensional vector space, and then you take I to be the set of subsets whose elements are linearly independent. That's one example of a matroid, an independent system, and in particular matroid. Okay, so another one, this one sort of closely corresponds to Kruskal's algorithm. In fact, is if we're given a finite connected graph, and then we take as the ground set of the matroid the edge set of the graph, and then the independent sets are the sets sets of edges which give spanning forests. So such that VA is a forest. And that's another matroid. Okay, and this matroid is called the graphic matroid of the graph G. Okay, there's another kind of matroid. So there's something to check here, by the way. I mean, the thing to check here is something you see in a first linear algebra class, which is that, you can, if you have two, what I said, if you have two sets of linearly independent vectors and one is bigger than the other, then you can, there's some element in the bigger set you can add to the smaller set and maintain independence. For graphs, this is saying if you have two forests and one of them has more edges than the other, then there's some edge from the bigger forest that can be added that joins distinct connected components to the smaller forest. So you could add it and maintain that you see a forest. Okay, so that's maybe obvious to you, maybe not, but either way, it's a fact that's required in order to verify the conditions of being a matroid. Okay, a third matroid, which is also based on, or class of matroids, also based on graphs. So again, we'll take a finite connected graph, and then the ground set of the matroid will be the edge set. And now the independent set, the independent system will be so sets of edges with the property that if we remove the edges, if we take away the edges, then we still get a connected graph. Okay. This is this turns out to be a matroid. And for these two examples, well, first let me say this gets called the bond matroid of G. Okay. What are the basis elements? What are the bases of this matroid, of the graphic matroid? So these are the spanning forests to which it's impossible to add any more edges while still being a spanning forest. So these are just the spanning trees. Of the underlying graph G, or more precisely, the edge sets of the spanning trees. Okay, but I'm just sort of thinking of the edge sets and the graphs as being the same for the moment. Okay, and in this example, what are the maximal independent sets? So that's sets with the property that if we remove them from edge collections of edges such that if we remove them, we still get a connected graph. But if we remove any more, then we get a disconnected graph. Okay, well that means that we must have removed so many edges that all that's left is a tree, right? Because if if when we remove a set D, there are still cycles in what's left, then that gives us additional locations where we could remove edges, and we wouldn't have a maximal independent set. Okay, so so here the set of bases is the set of edge sets D such that V E minus D is a spanning tree. Okay, so maybe if I'm a little more precise, it would be a good idea to be a little more precise up here. Here I could say that it sets A of edges such that VA is a spanning tree of G. Okay, and so you can see that these two structures are pretty closely related to one another, right? Here here the independent sets are the edge sets of spanning trees, and here the independent sets are just the complements of the edge sets of spanning trees. Okay, so this is called the dual matroid. This bond matroid is the dual matroid of the graphic matroid, and so the definition is for a matroid Xi, the dual matroid is so X with independent sets now given by the complement of the original independent sets. Okay, so I'll leave as an exercise. So if X is finite, then the dual matroid is indeed a matroid. Okay, that might also be true if the ground set is infinite. I just haven't thought about it carefully enough. Okay, but it's certainly true for finite ground set. Okay, and you know, there's something, I guess implicitly there's also an exercise in here which you could prove either by proving this general exercise, which says that dual matroids are always matroids. If you that would in particular establish that the bond matroid is a matroid because the structure is clearly dual to the graphic matroid. Okay, but if you don't prove it by proving this general fact about duality, then you need to check the matroid property, which says that if I have two sets of edges, each of them leave the graph connected if I remove them, but one of them is bigger than the other, then I can take an edge from the bigger set and put it in the smaller set, and that still has the property that it leaves the graph connected. Okay, so there's you need to check the augmentation property holds either for this matroid either directly or by verifying that dual matroids are always matroids. Okay, so so let me give you a couple more. Well, first, is the definition of matroids clear? Any questions about that? I'm going to leave you with a couple exercises about them. You know, if they turn out to be a surprisingly rich structure. There are a lot of unanswered questions about matroids, general structure theory. I mean, I'm not an expert, but they, you know, in a sense, they generalize graphs, and so there's, in a way, as many questions about matroids as there are about graphs. But I'm not going to be going into full generality. You know, Whitney's paper on them, where he introduced them, has like 2,000 citations or something, and they were also studied in the early days by Saunders MacLean, who invented category theory. Now took them in a different direction, which I know very little about, but I just want to focus on their connection with Kruskal's algorithm. So, you know, that's not going to take us very far afield. But let me leave you with a couple exercises about sort of basic matroid facts before we focus in on Kruskal's algorithm. So these should all be, you know, sort of, if you just think about vectors in your mind and independent linear independence, then you can see how all of these generalized properties of vectors. Okay, so in a matroid, any two bases have the same size. There's the basis exchange property, which is sometimes used as a definition instead of the augmentation property. So for any two bases, A and B, there exist A and B, such that A minus A plus B is another basis. And I think this one is correct. So if B is a set, a non-empty set contained in 2 to the x for some finite set x, and all elements B have the same size, then B is the basis set of some matroid. A little skeptical about that as I write it down. I thought it was true when I wrote it down. Yes, and there is a correction, thank you. Okay, so some of those I explicitly set for those of you who are sort of trying to follow along with exercises, but they're in those are given as references to the typed notes, which are on the website. So you can look at that. Right, so now I'm having defined matroids. I'd like to generalize Kruskal's algorithm to the setting of matroids. So it's really just the same process. But now we need, so as input, so some independent system. And then some weights, which will be weights for the edges of the graph. Well, so it was edges of the graph. So here it's elements of the ground set. Okay. And the procedure is really exactly what you'd think, given that I'm calling it Kruskal's algorithm. So we'll list the elements of X in increasing order of weight as X1 up to XM. So using M for the size of the ground set. And I said it was finite. So, so then we'll start from an independent set with no elements. Okay, and then we'll just consider the elements in increasing order of weight. So for each I from 1 to M, if we can add xi to the independent set we've built so far, so if that's another independent set, then we'll add that xi. So we'll set I sub I to be I sub I minus 1 union xi. And otherwise we won't add it. So then I sub I is equal to I sub I minus 1. Okay, and then finally we just output the whatever we get at the end, IM. Okay, so we consider the atoms of our independent system in increasing order of weight, and we add them greedily whenever we can, while maintaining that we still have an independent system. Right. So yeah, I will. There are some questions in the chat. In the third exercise, we need to assume the basis exchange property on our collection of bases. As I said, I mean, suddenly, as I was writing it, I felt like I was. It didn't seem true to me. So let me not try to comment on that right now. I'll think about it and fix the exercise in the notes if there's a problem with the version in the notes. I don't think it's right as I've written it down. Another question: do we assume the weights are distinct? Yeah, let's. No, I don't think I do want to assume they're distinct this time. So this is just this is some list in increasing order of weight. Okay, it's actually useful in what follows not to assume they're distinct, but just an arbitrary non-decreasing order of weight. Okay, so the output will depend on the precise choice of order if the weights aren't all distinct. But they'll still be so all non-negative. Okay, so So I'd like to understand when, this is going to output something, and I'd like to understand when that something is a minimum weight basis for a matroid. Okay, but before I even get to that, for the moment I haven't assumed that there's a matroid structure. I've just said we have an independent system. So let's think about what we can say without any further assumptions. Okay. So the first is that if I look at one of the things that wasn't added. So if I look at indices I and j between 0 and m, so if xi is not an element of ij, right? So if that means xi wasn't added when it was considered by Kruskal's algorithm, it didn't get added. Then that means it also isn't, because this is an increasing sequence, it also isn't in I sub I. Okay, so why does, so isn't in I sub I. Why does an element fail to get added? That means that xi, that adding it would have broken the independence property. So xi minus, if we take I sub I minus 1 and add xi, we leave the collection of independent sets. Okay. And now, because an independent system is downward closed, if this, if this isn't in I, then ij union xi also isn't in I, right? Because ij is bigger than ii minus 1. So if this were in I, then by downward closure, this would also be in I. Okay. So in particular, that means that if xi is not an element of the, so if we look at one of the things that's not in the output of Kruskal's algorithm, so if xi is not an IM, then that means that we can't add, I'm just taking j equals m up here, we can't add xi to the output and get an independent set. Okay, so then, so IM union xi is not an independent set. Okay, so that's saying that if we look at the output and we look at the things that the atoms that are not in the output, then we can't add any of them and maintain the independence property. Okay, so that means that the output is a maximal independent set. Right, and so it's a basis. If we're in the setting of a matroid, we call those bases. So. Okay. So, so I'll state two theorems and I'll prove one of them. So the theorem is that for matroids, this algorithm does indeed output a minimum weight basis. So for any finite matroid, non-negative weights W. So Kruskal's algorithm outputs a minimum weight basis of M. And if the weights are distinct, then that basis, and the minimum weight basis is unique. Okay, so that's the first theorem. I will prove that in just a second. The second theorem I won't prove, but the proof is in the notes. This says that this connects Kruskal's algorithm with the definition of matroids. So if you give me a finite independent system, then it's a matroid if and only if Kruskal's algorithm always works. So Kruskal's algorithm outputs minimum weight basis for any choice of non-negative weights. Okay. So in other words, that's saying that among the class of finite independent systems, the correctness of Kruskal's algorithm for arbitrary non-negative weights characterizes matroids. Okay, and in the proof of that, you actually need to allow, well, you probably don't strictly need to allow, but the proof is cleanest if you allow equal weights. You could, when you read the proof, you'll see it writes up most cleanly if you are allowed to repeat weights on some of the atoms. You could tweak it to use distinct weights, but it would be uglier. So that's why I didn't assume distinct weights in this section. Okay, so as I said, I'm not going to prove this. I will prove this. Okay. In a way, I mean, well, the proof of this, makes the previous proof of the correctness of Kruskal's algorithm I gave a bit redundant because that was a special case of this result. But I think it's still worth having done the most relevant important special case separately. But let's now do the more general result. So I want to show, I'm trying to show that the greedy algorithm, Kruskal's algorithm, outputs a minimum weight basis when applied to a matroid. And so I'm just going to argue that if I take any other basis than the output, right? What's the output? We called it IM. So I'm just going to show that any other basis than IM has weight at least as large as IM. And if the weights are all distinct, then any other basis actually has larger weight. And that will prove the theorem, right? So let's fix some other basis. So A is not the output I sub M. Okay. Then I claim that if I look at the number of elements of A among x1 up to xm, so among the first, x1 up to xi, so how much of A falls in the I lowest weight atoms, that's at most as big as it is for the set that's constructed greedily. Okay, so this is saying when we greedily add elements to our independent set, we get at least as many elements as we do in any other independent set by any given time. Okay, and that should be true for all I at most m. Okay, and this is just a consequence of the augmentation property. Okay, so if not, that is to say, you know, if the size of, if A has more elements among x1 up to xi than I does, right? Then, so by the augmentation property, that means we can add some element of the set on the left to the set on the right and get a bigger independent set. Okay, so there exists x in this set such that adding x to I sub I gives us another independent set. Okay, but we already ruled that out, right? That was the first remark I made. I said that anything that we didn't add at the moment we considered it, we can't add and remain an independent set. Okay, so that so that's not so. So this contradicts remark 1. Okay, so that says that's really the heart of the argument. It says that the greedy algorithm, you know, adds at least as many elements as any other as it goes along as any other independent set can have. Okay, so now having made that observation, let's just list the elements of this other basis A in increasing order of weight as you know, A1 up to AN, I'll call it. So all of the bases in a given matroid have the same size, and I'm just calling that size n. Okay, and I'll also list the elements of IM of the greedy basis in increasing order of weight as let's say y1 up to yn, right? And the claim tells me that these, in this increasing order of weight, the elements of IM come along sooner than the elements of A, right? Because A has fewer elements in any given initial segment of the order than I does. Okay, so just pairwise comparison, all of the weights in the A sequence have to be at least as big as the weights of in the Y sequence. So by the claim, the weight of AI is at least the weight of YI for all I and N. Okay, so so that tells me that the weight of A, which is just the sum of all the weights of its atoms, is at least the weight of I sub m. Okay, so that says that Kruskal's algorithm does output a minimum weight basis, and if the weights are distinct, then at least one of these inequalities must be strict, right? Because the only way you could have exactly the same, if all of these if all of the AI are bigger than all the YI, then the only way the sums can be equal is for all of the values to be exactly equal. But then that would mean that we actually had the same basis. And we started off by assuming that they were distinct. Okay, so if all the weights are distinct, then in fact, the weight of A is bigger than the weight of IM. Okay, and so that says that when all the weights are distinct, IM really is the unique minimum weight basis. Okay, so the last, any questions about that proof? I have one more thing I want to say and then we'll call it a day. Okay, so the last thing I'd like to do is a special case. So we went from the this special case of Kruskal's algorithm to the general case of Kruskal's algorithm on matroids, and now we're going back to a special case, which is Kruskal's algorithm for the bond matroid. of a graph G. Okay, so remember that the bond matroid was the matroid where the independent sets were the sets we could remove from the edge set while still remaining connected. Okay, so now the minimum, what are we going to be doing there? We're going to be removing edges one at a time greedily, in order of weight, and only removing each edge at a given step if its removal leaves the graph connected. Okay, so we try to we're removing it. Yeah, that's what we're doing in the dual. So in Kruskal's algorithm applied to the dual. So that algorithm is called cycle breaking. Okay, so the input is a finite connected graph. G. And weights W, as usual, weighting the edges. And so then the steps are, we order the edges in, well, I'm going to write increasing, but I'll return to that point of weight as, you know, actually, let me swap this right now. So if, formally speaking, Kruskal's algorithm on the dual graph is just going to do exactly the same thing. Order the edges in increasing order of weight and remove them one at a time as long as removing them leaves the graph connected. But if we're interested in minimum weight spanning trees, it's actually nicer to order the edges in decreasing order of weight rather than increasing order of weight. Okay, you could always just, you know, take some huge value bigger than all the weights and subtract the weights from this huge value to swap the order from increasing to decreasing. Okay, so that doesn't really make much of a change. But so let's order the edges in decreasing order of weight, and I'll write them as em minus 1 down to E1, just to make it clear it's sort of the reverse order from before. And then we can start from the set of edges, which is all the edges. Okay, and then for I from m minus 1 down to 1, you know, if removing edge EI from whatever graph we've built so far leaves the graph connected, then we remove it. So we set EI star to be EI plus 1 star minus EI, and otherwise we don't remove it. So we set EI star to just be EI plus 1 star. Okay, and so we're greedily removing edges, if you like, and then we output the graph with edge set E1. Okay, and so then the output is, because I swapped sort of increasing and decreasing, the output is a minimum spanning tree of G. And so if G is, if the weights are all distinct, then it's the minimum spanning tree. Okay, so so that's two different greedy algorithms for building the minimum spanning tree. They both actually come up in our probabilistic analysis. The idea of adding edges greedily or removing edges greedily. They're both global procedures in that they look at all the edge weights and sort of greedily make a choice among all of the edges that haven't been considered yet. In the next lecture, we'll start by introducing a local procedure which only looks at sort of growing a tree starting from a single vertex and adding one vertex to a growing tree at each step. That's PIMS algorithm. And then we'll start to use PIMS algorithm to understand the structure of minimum spanning trees on infinite graphs. But on infinite graphs, there are various challenges with all these algorithmic definitions, and you need to think a bit more about how to make sense of them. So we'll talk about that. I see a couple comments in the chat. I think I addressed the most recent one. The one before, did we already prove somewhere that all bases have the same number of elements? I didn't prove it. I think I might be stated as an exercise, but the point is basically the augmentation property makes it quite easy to see that all bases must have the same number of elements. So if you have two independent sets and one is bigger than the other, then the smaller one can't be maximal, because we know that there's something from the other one you can add to it. Okay, I'll stop the recording there and take questions.